Yeah.
That are not tabulations, right?
Right. No, but actually, I'm talking about an application of
Elements
sorts.
for nonlinearly damped global tide models.
Great. So I'd like to thank the organizers for a great conference and everyone for great discussions that we've had over the week. So this is, I guess, the last session. So this is going to be some joint work I've done over the last several years with Colin Cotter and some other people, kind of getting back to my roots. I worked on mixed finite elements in my thesis. And so this is kind of a neat problem that I'm going to tell you about. It's also joint with Lawrence Mitchell from some of our solvers and a colleague who is not a numerical analyst, but a PDE guy at my university. So let me start out with the second order wave equation that we all know and love. So right, it is what it is. And so the fundamental thing about this is that it's an energy conserving system and it describes a lot of things. You can also sometimes think about it, and I do, as a first order system of equations where here U is going to be some kind of velocity and P is going to be a scalar pressure. And when I see things that have divergence on them but no curl or no gradient, I think that you should be using mixed finite elements. So, so one of the fundamental things we have here is you can multiply both sides of the equation like you do maybe in a PDE class, and you can integrate, and you'll see that a thing that is like a kinetic and a potential energy, a total energy of the system differentiates to 0. But you can also see something about this in the first order form. You can multiply this one by P, this one by U. After you integrate and then integrate by parts, these things are equal and opposite sign, and add them together, and you will come up with a slightly different conservation principle. So those are the most fundamental thing that we know about energy equations. And this is really pervasive in wave phenomena that we see, time-dependent Maxwell's, tidal model, shallow water equations, et cetera, et cetera, et cetera. So the thing that I'm going to focus on is tide models, and a particular kind of linearized tide model. Okay, so here it is after you do a bunch of work and you do some non-dimensionalization. So the U is a fluid velocity that you have. It's actually a momentum. And the eta is the linearized height, so the deviation around what the average height is. And so you get these time derivatives, you get these derivatives in space, and you also get this U perp term that comes from the Coriolis force. You get some kind of quasi-periodic driving function like the moon and whatever else is forcing the oceans. And you also get this model G of U, which is a damping term. And is really interesting. The rest of it is a simple perturbation of the wave equation, although when you want to do analysis, and in this talk computation, figuring out what that G is and how you handle it is somewhat interesting. Okay, so by the way, if you cover up the damping and the Coriolis terms and you relabel the variables, it really just is back to the acoustic wave equation that we know and love. Okay, so what is the G? A few years ago, Colin and I wrote a paper. If the G modeling your bottom friction is just directly proportional to the velocity itself, it's like a damped harmonic oscillator, and you can show kind of exponential energy decay in the system and get some nice estimates. More recently, we have a paper that's it's up on the archive, and someday I'm sure will appear. It's been revised several months ago. You can think about power law type things, and now the damping is in fact degenerate. So if you think about what the like the marginal damping rate is as the velocity itself goes to 0, the damping itself goes to 0. And so the theory, like doing your energy estimates for PDE and doing your finite element error estimates and your stability theory and everything else gets a lot more complicated. And that's really the purpose of that paper that we've got up. So typically we think about P as 2, which is called quadratic damping, because then it's U times the modulus of U, or maybe cubic damping. So those are interesting things. And so, as I said, the relative damping rate goes down as u goes to 0. Now, so weak form in finite elements, we're going to multiply by test functions and integrate. And so you get all of this. And then you want to find functions u and eta so that this all holds, right? So finite elements, well, not quite 101 because it's going to be an HDiff. So what we will want to do is use a space for our etas that are discontinuous polynomials of some degree k, and our velocities have to contain at least polynomials of degree k, but one of the magic things about mixed finite elements is you've got to pick them so that you have this magic commuting diagram property, and if you know about mixed finite elements, this says this is worth 1,000 words, and if you don't, this and 1,000 words will just start to crack the surface. So, so the important thing is you can't just use polynomials in regular degrees of freedom. You have to pick magic spaces so that if you take the divergence of something and then do the L2 projection, that's actually the same as if you had a magic interpolation operator into your velocity space and then discretely took the divergence. So we have to use some special things. Like the Ravier-Thomas space. This is somehow the smallest space that works. If you take the divergence of these things, this is the x vector, you wind up just being onto pk, and you can pick the degrees of freedom in the right way. There's also some slightly larger spaces that we can pick. So we're going to use Firedrake, and so it just magically happens that we can get the right spaces. It is also the case that we did all of our analysis by coming up with a second-order primitive equation that actually is completely consistent with the equation, although we're going to compute with the first-order system. But an amusing fact is that the commuting diagram property means also that discretizing the primitive equation is the same as discretizing the first-order equation and then finding a discrete primitive for it. Those actually turn out to be the same thing, and so we can do all of our energy analysis and such. But so the interesting thing here is if you pick if you kind of pick the test function to be appropriate, you see that the energy now has got to be non-increasing. Because the g we're going to assume is a monotone function, so I've got the time derivative plus something that's positive is equal to 0. And so if you go read the paper, you can show that if you turn off all of the forcing functions, it's not easy, but you can actually show that the energy will decay at a special rate. It'll be exponential if you have linear damping, and but that's true. Okay, so the theory, we can actually show several things in it, which is kind of neat from an application standpoint. We can show that there is a global attracting solution for the PDE, which justifies this thing called spin-up in tide models, that, well, we don't know, if you want to do the second millennium and study the climate for that, well, you don't know what the tides were doing at the beginning of the second millennium, so you can start at some point in the past and let them run. And if you start long enough back, then you've got a pretty good initial condition, as I understand it as a math person, what that means. And so we've also got some really neat finite element error estimates. And so if we compute out of our Firedrake code, which I'll show you, you can show damping rates. Well, this is actually truncation error from using Crank-Nicholson. And you'll get different kinds of damping rates as you use different kinds of damping profiles. And so these things kick in. We get synchronization of solutions. And if you want to see what this looks like on a,
Because you didn't upload the video.
I didn't upload the video. It's not embedded in the PDF. So it's kind of sorry. So we're going to do all of these calculations in Firedrake. We've seen some of this in a talk, but I'll remind you. So it's an automated PDE system, primarily developed here at Imperial, although people other places certainly contribute to it. If you know Phoenix, it's got this beautiful Phoenix-like Python interface. It is also nearly a pure Python implementation. It's Python all the way down, except where it's not. And there's a couple of core places for performance. And so the main thing I'm going to look at is how to solve the linear system using the kind of solver infrastructure that Lawrence talked to us about earlier. And I'm going to use it. So here's an example. set up, I left out the imports and the defining a mesh and everything. But here is a complete description of the Crank-Nicholson time stepping. Why do we use Crank-Nicholson? Well, it's second order accurate, but more importantly, it's energy conserving on this model if the damping is turned off. And so it actually does well for handling the energy decay as well. We set up a nonlinear variational problem based on this nonlinear description of our equations. And we build a solver. And, well, to make sure that our damping and everything works, we can say we're just going to blast everything with LU factorization on assembled matrices. We'll assemble the Jacobian at each time step and just smack it. And then we can loop over our time steps, solve the problem, update, and away we go. So maybe you've noticed this if you do. So if you're wanting to do implicit time stepping and you want it to really run well or run at scale, LU is probably not your friend. And so if we look at what the linear system looks like and say, how can we get an iterative method for this? Well, you'll get this kind of block system. So this D and D transpose are the weak divergence operator. M is nice because it's a mass matrix on the pressure space. So if you're using lowest order elements, it's just diagonal. And M tilde is a mass matrix on the HDiv space. M tilde perp is the inner product of basis function with the perp of the basis functions. So it's kind of like a mass matrix. It's a little weird, but doesn't behave too badly. And so we want to come up with a good preconditioner for this sort of system. And there's really two ways of going at it, but an important thing, there's a typo on this slide. I've left off the imperp term. It doesn't really complicate matters, but if you look at the Schur complement, this operator here is, morally speaking, a Laplace operator. Okay, and then this is a mass matrix, so this is really like a Helmholtz guy, the good Helmholtz operator, with a large, shift. And then you get this other funny thing that's the Jacobian of the damping term, which could be nonlinear. It's not bad, but it is kind of a semi-definite, not elliptic operator. But the trick here is we can't just bang on this because M tilde inverse is dense. So we have to look at other ways of coming about with preconditioners. Okay, so if you've seen the Mardal Winther preconditioning systems of differential equations paper, you could think about somehow, if you think about this is an operator on L2 cross H1, you can think about if you use this sort of operator as a preconditioning operator for the system, that ought to give you something that's mesh independent. But you can also think about it as, well, I had an HDiv operator, and I'm only really doing mass matrices in the bottom corners, so maybe I could get away with something like this. So we'd like to be able to play with these kinds of preconditioners inside our solver and say, can we make one of these kinds of approaches really robust? And so I don't want to just build it and solve it, but I also don't want to go code up all of these different crazy operators and see how they work. So the trick is that Firedrake is going to save our bacon, as it were, and we can write all of these extra operators, Laplacians and the div operator and things in UFL, and then feed them to the preconditioning infrastructure. Okay, so Lawrence and I had this paper that appeared earlier this year. And so PETSc gives us, so like all of the work on field split and algebraic composition, PETSc gives us a great job for taking existing solvers and gluing them together and putting them inside of each other in all sorts of creative ways. And we've seen a lot of that on display this week. And then Firedrake is great for building these kinds of extra differential operators that we have. Okay, so as you recall, what we did is we created a new Python matrix type that does two things. One, it just assembles the action of the operator as a matrix-free thing, but it's also a bucket that has all of the symbolic information we use to generate the code. And so it is a place that new preconditioners that we write in Python can reach into, fish some stuff out, import Firedrake, and do whatever we need to do. Okay, so I like this picture. So this is the level we're working at with this matrix-free matrix, right? So you don't have to actually go change the public interface, and write special purpose code. We can use the matrix-free matrix as a bucket, or as an extra channel besides the public calling interface. So anyway, so one exhibit that we would like to do is, suppose we do want to just invert the Schur complement and work on that. Or, so if we did the Laplace operator, ignoring all of the extra terms and the time stepping, you can take the Laplacian, and instead of having that ugly saddle point problem, you can write an even uglier one that is got an amusing feature. So if the UH, VH, are now in a broken HDiv space, so they don't have any continuity between any elements. Okay, this is your local conservation equation. This is your local constitutive equation, but now you get a jump term in your test functions, and you multiply it by some kind of magic Lagrange multiplier that's supposed to model the pressure on the edges, and then you assert that, oh, after all, I was in HDiv because I don't have any jumps between the elements. What is true about this kind of discretization is you get the same UH and PH, or eta, is in the wave equation that you would have if you had just written down the original second order, written down the original block system. But you can actually locally eliminate all of these things, just element-wise calculations, and get a symmetric positive definite matrix that's sparse for just the lambdas, and then reverse the process. So that's really nice. It'd be nice if somebody implemented that, because that looks like a pain once I've already written my wave equation code to go and then implement some new method just to do it. So,
Okay. Thomas's punchlines.
Okay, so he was asking. So anyway, so Thomas is going to talk about this, and I'm going to talk about an application of this. He's got this wonderful package Slate that will do just what I said. So it will go and sniff out HDiv functions, as it were, and it says, oh, there's an HDiv function here. And then it will break the continuity, augment the system by rewriting the linear system with Lagrange multipliers, and it will automatically do all of the black magic for us. So when I started out like that to make sure I was getting my energy damping equations and everything right, I had those solver parameters. Now, if I want Thomas's magic, all I have to do is say, oh, I didn't want to build my matrix after all. I'm going to feed it to Thomas. And inside, I said you've had a symmetric positive definite system for the Lagrange multipliers. Well, do what you think is right for an SBD system. Okay, so another beautiful thing, and it just works great. Another beautiful thing that I was able to do and play with in this is, right, this linearity is interesting from a math standpoint, but it's not too bad computationally. So what I was able to do here is, if I just let Thomas do his magic, said, well, I've got to take about 3 Newton iterations per time step, which is good. Maybe that means I need to take a bigger time step so I can take a few more Newton iterations. But then at each time step, I had to do 7 GMRes iterations. 7 CG iterations using GAMG inside of the Krylov, inside of each Newton step. But it's so brilliant. You can just play with the options. Well, what if I don't actually solve that inner system, but I just hit it with the sweep of GAMG? Well, what happens there? So now my KSP type is going to be pre-only, but inside my Schur complement system that I build, I'm just going to do pre-only there. Okay, so it doubles the number of Newton iterations, because right now I'm doing it inexactly. I'm not actually solving the Jacobian system, but I'm just applying a preconditioner for the Jacobian system. So that's like 6 linear iterations, as it were, as opposed to 21 iterations. And this was all for free from the comfort of my own command line. I didn't have to rewrite any new algorithms, and I get a very fundamentally different process that turns out I can explore with. One other feature, and it looks like I'm about out of time. So if you want to precondition the mixed Laplacian, well, Hyper, I've heard a lot about Hyper. They also have this thing called auxiliary Maxwell and AMS and ADS. operators, and they provide algebraic multigrid for operators like this. So if we're doing this kind of Mardal, Winther, HDiv, Riesz map preconditioner, well, Firedrake will let us discretize that and get a matrix, but you need some other things. You need to be able to sniff at the mesh and say what's the discrete gradient, which has to do with the edge to vertex incidence relations, and you also need the physical mesh coordinates. So not only now does Firedrake need to build some other operators, well, we need to actually query for runtime information. So the user doesn't have to, I'm the user in this case, I don't have to go look at my code and add some stuff in it and then say, if-def it out if I really wanted to use a different method. I can just put this all wrapped up in a tidy little preconditioner, and I never have to set the coordinates or anything because the Python thing fishes them out of Firedrake and sets up the hyper PC for us. This isn't released, but I'm glad to share it with anyone, and maybe I should just put in a pull request to Firedrake on it. There's a few things we want to add into it, but you can just do stuff like this. It's not great yet. What happens is that as delta t changes, my iteration counts are varying very wildly. So I need to do some work on what they call robust preconditioning for this, which is where you kind of change the relative weights of all of the terms in the Riesz map, and you can, if you do it right, but this is in progress, so I haven't done it right yet, you'll be able to get not only mesh independent iteration counts, but ones that are also independent of the delta t. So that's some stuff that I'm working on now. And I've got a few references in here if anyone wants to see them. So thank you very much.
Any questions for Rob?
Toby.
Okay, the inexact division solve, I just wanted to point out to people that can be made robust already with SNES, with the Eisenstadt Walker type of.
Okay. Okay.
So you don't, so just for the benefit of other people in the room.
Including me.
If you want to do this sort of thing where you do your linear solves and using Krylov very inexactly because you don't want the linear residual to go down to 0 because it no longer reflects the nonlinear residual. It's called Eisenstadt Walker choosing the residual choice for the linear, and it's already in SNES, so
Okay.
that's available.
I was just doing a preconditioner. I wasn't changing my inner iteration tolerance. So.
Right.
So this is even less exact.
You just chose, let me do one PC application. So you were doing it without really seeing what the residual would be after.
Okay.
And so that worked for you, but I'm saying you can make it robust and get kind of the benefits of reduced linear solver time.
Okay. Great. Thank you. I appreciate that.
You still get CG magic. I mean, you still get Krylov magic.
Yeah,
Just
okay.
one iteration.
Okay. Great.
So does Firedrake now has support for computing discrete operators for any order, or the discrete gradient you are computing just from the mesh vertex? Can you do the discrete gradient with higher order spaces? Or
I haven't. Okay. So I have.
I think I don't understand
It's the discrete gradient you need for AMS.
so pretend I don't know AMS because that's a good
Okay.
start.
So
no,
are you asking about the discrete gradient in AMS?
I'm asking how Firedrake computes the discrete gradient.
Okay. So right.
For higher.
So that's not a Firedrake feature. That's something we wrote. So meaning a student. So just kind of tossed together, and it just looks at the edge vertex incidence.
So hang on, I'm a bit confused here. Can someone explain to me what the question is, and then I might be able to answer it.
So, yeah, there's a discrete gradient operator. Yeah.
For example,
The
they
gradient
have
of
like
what?
MFAN, right? They are
Sorry?
MFAN.
Okay.
For example, they are able to construct these discrete operators
Mm-hmm.
So the discrete gradient
in two different spaces.
Yes.
Irrespective of the order. If you are on second order, it's not so natural.
Yeah,
It's
so-
not -1.
So we wrote a little loop over the mesh. That's all that we did. One could, yeah. So we did it. It's actually I did it a PyOP2 kernel. So it's the gradient mapping an H1 function onto the Netlink space. Lowest order.
How you map H1 in your space.
And it turns out to be So on a triangle, it's a little 3x3 matrix that's either 1 or -1 or 0, depending on the connectivity of edges to vertices. We haven't done it for a higher order case. This is kind of a one-off, look what we can do thing. You could do it, worst case, you could do it generically by taking the gradient in UFL and projecting the gradient onto the Nedelec space. But that's pretty, yeah, so we could write it that way. I just wrote a little PyOP2 kernel that spins over the mesh and builds the discrete gradient for the lowest order case. Yeah, yeah, so we're doing that. One could, it would go from like one kernel to something like that to do the projections if we wanted to. I just haven't. There's not a whole lot of motivation for doing algebraic multi-grid on fully assembled stuff at high order. So we just did the lowest order case and did something that worked.